Oh, good, that seems to be working. I'll give you a couple minutes on that whilst I struggle with figuring out how this thing turns on. Oh, wait a minute. Power. Uh-oh. That was probably this one. Whiteboard screen. Yeah, it's not even giving me the possibility of the document camera. That's going to be real bad if I can't get that to work, because these, well, especially, I mean, even if the camera were on, look how tiny everything is. So I'm not really sure what I'm going to be able to do. Still, let's say another 45 seconds or so. I want to make sure that everyone responds who wants to. Oh, by the way, please don't put E. E is not the right answer in this case. Oh, this has stopped blinking, so maybe we're good. Oh, I know what it is. You know, is it integrated webcam? No. Well, I feel like I'm getting closer, because if the problem is the camera, then I should be able to change this to the document camera. If the problem is the connection's gone, then it's bad. In that case, I'm going to have to think quickly and try to get some pictures off the internet of what I'm talking about. And I guess that could be better than nothing. So we'll go with that. Good, so let me stop the responses here. Good, so remember, man, that's so loud. They don't allow you to change the volume on this thing. Oh well, this is going to be one of those days, I'm afraid. I feel, how can there be feedback? Where is there a speaker? Oh well. I trust that at least my voice is clearer. It sounds clearer to me. And the reason the face shield, as long as I stand behind the plexiglass window, of course, and am more than 6 feet away from you, then I'm following the rules. The reason this isn't potentially better is also for those who might have difficulty hearing and rely on being able to read my lips. So I think it's going to be better if you guys are okay with it. Good, so remember the rules for arrow pushing, and we've gone over them already. The rules are that the arrow always starts where the electrons start, and the arrow always ends where the electrons end. There are no exceptions. That's always going to be the case. And so we want to show formation of a new bond between chlorine and aluminum here, right? And we want to show the electrons in that bond coming from one of the lone pairs on one of the chlorines. So we need to find an arrow that starts at one of the lone pairs on one of the chlorines and ends around the vicinity of the aluminum atom to show that we're going to form a new bond. Does that make sense so far? So let's try to find one. This one's no good. It's starting at the aluminum, that's exactly backwards. This one is going to turn out to be the right answer. Although, of course, if you started the arrow at any of the other 5 electron pairs, really, it would also be fine. It would also be accepted. Does that make sense? Yeah, it's not a different answer. It's the same answer. This one might be close, except you're also breaking the bond between chlorines at the same time. And this one is what I think you young people call a hot mess. So I think the correct answer is B. I may even be able to check that. Let's see. Oh, good. I just marked that as correct. That's good. Any questions then, either in chat or from the live audience. If not, then let's go on to our next one. Which of the following is the generalized structure of a carboxylic acid? And when all else fails, follow the directions. Do I need this Camtasia? No, that's different. Yeah, that doesn't really help. Tell you what, while you guys work on that, let me turn off my mic and call the helpful people who come and fix things. Okay, help is on its way. Anyone, oh, it's been well over 2 minutes. So hopefully this was fairly straightforward. All of these are perfectly good abbreviations, but there's only one that's for a carboxylic acid, and that would be A. So hopefully that was relatively clear. Yep, looks like that went just fine. And like I said, you'll get the other 8 points for attendance. So that should do it for us for the clicker session. Let me close that down. We'll go back to sharing the whiteboard since that's what we're mainly going to use today. And I think that's about it. So I'm trying to think if I have any other announcements. I guess I kept you guys apprised over the weekend. Again, I made some minor changes to the syllabus. I may still make some little changes as the semester goes on, but like I said, it's not going to be dramatic changes. I'm not going to suddenly go, oh, here's 2 more exams that we're going to be taking or something like that, you know. Okay, so today we need to go over naming alkanes, and that's going to be a topic that largely the best way to learn it is by practicing, and you will get lots of practice in OWL. This is also a time where, quite understandably, I get a lot of questions about what the questions I give you for nomenclature will be like. How hard will they be? What will be the parameters? What's the limit of difficulty I will have? I understand wanting to know all that, but it's not something that I can describe in detail. I feel I've already gone pretty far in giving you old exams so you can get an idea as to that. I will say that I will never purposely ask a question that does not have one clearly best answer. That's always my goal. I don't recall really screwing up too badly, at least on nomenclature questions. lately. Now, OWL will always try to push the envelope with you guys. OWL is always going to try to test the limits of the rules, so to speak. And I think that's okay. I think that gets you used to what some of the parameters are. But that being said, now I think we already went over, didn't we? Someone's asking about the reef questions. I mean, shoot me an email and we'll take care of that later. But somehow we need to get that reef app working. In order to answer questions on reef, you're going to have the pay app, which I'm told is something like $16. The free app only works for attendance. So, I understand these, thanks. These technological difficulties are tricky at the beginning. But in any case, what was I saying? I was talking about nomenclature questions. So like I said, you can see examples of past questions I've asked. I think it's important to be able to go from structure to name and name to structure. I've always found that going from name to structure is a little easier. Maybe that's just me. Couldn't a carboxylic acid also be RCOOH? Yes, absolutely. That's also perfectly acceptable. But of those 5 answers you were given, that was clearly the best answer. But yeah, RCOOH is perfectly acceptable. And you can write out what R is. If you want to write acetic acid, you can write it as CH3CO2H or CH3COOH. Both are perfectly acceptable. Both would result in full points on the exam if that was the answer to a question. Does that clarify that enough? Is everyone okay? This is way too loud still. Okay, so yeah, so if you had trouble in answering the reef questions, please let me know. Excellent question in chat. Since COOH contains OH, would it be considered an alcohol? Great question. Answer is no. And the way you know it's not an alcohol is by the definition we gave of alcohol. We said that an alcohol, oh, I guess I can write on this now. An alcohol, we defined it as ROH. And we said that the carbon that's attached to the OH needs to be a hydrocarbon type carbon. It needs to be an alkyl type carbon. And because once you have the carbonyl over here, this carbon that's directly attached to the OH is no longer a hydrocarbon type carbon because it's double bonded to oxygen. That means that it doesn't fit the definition of alcohols. So carboxylic acids and alcohols are different critters. Oh, sure, they have some similarities, but they are different critters. So that's how you know. If the carbon attached to the OH is C double bond O, it is a carboxylic acid. If not, if it's just a hydrocarbon type carbon, then you've got an alcohol. That's an important question. Does that make sense? Does that distinguish that clearly enough for you guys? Good. So that being said, where were we? We were going into naming alkanes. So in your class notes, I've given you a step-by-step method that you can use that should always unambiguously bring you to the best name for any given alkane. And it's not the only way to do it. I don't say you have to do it exactly my way. You can feel free to tweak that to your liking. But it should always bring you to exactly one unambiguously best answer. And I am not aware of a question that could be asked that if you follow that method, you will not get to exactly one unambiguously best answer. I've never seen a question on OWL or on anyone's exams ever for which that's not the case. So I believe that you will always be able to come to the best answer if you use that method. Does that sound good? Does that make sense? I think that should have told him the mic was crazy also. So that's my opinion. I wish I had time to do a whole bunch of examples, but unfortunately I don't. So let's at least do one though. That's better than nothing. Oh yeah, let's go crazy. That's a good one. So that's one. And of course, you should also be able to draw that in kind of a condensed form. You don't have to use line angle drawings if you don't like them. That's fine, it's optional. But I do expect that you're able to understand them when you look at them. Another thing that I think I've said is you're going to need to know, let's say at least the first 12 straight chain alkanes. I think we went over that, right? The only irregular ones are the first 4, methane, ethane, propane, butane. And along with that, the alkyl groups that come from it. You need to know methyl and ethyl, and there's 2 propyl groups, right? There's N-propyl and isopropyl. And I think I also said you needed to know the butyl groups. I very much doubt you're ever going to need pentyl groups or hexyl groups. It's so rare that you actually need to use those in a name. And of the 2 butyl groups, there is N-butyl, sec-butyl, isobutyl, and tert-butyl. N-butyl and tert-butyl are the most common ones by far. You'll find us using them a lot as the semester goes on, especially maybe tert-butyl. So they're in the book, they're defined in the book. I've discussed them in my class notes also. Those, I think, are the only ones you'll need in order to answer any question either on OWL or in my exam. Good, so the rules state that you first need to find the longest continuous chain of carbons. The definition of continuous is that you don't pick your pen or pencil up off the paper, and you can just number it straight like that. So it may be tempting at first to say like 1, 2, 3, 4, 5, 6, 7, but I think we can find a longer chain if we start down here, and I think we get an octane. 1, 2, 3, 4, 5, 6, 7, 8. Or you could start on this one down here. Let me give you a visual aid by circling that chain. There we go. And obviously, if we had started at this carbon instead over here, we would get the same thing. So we already know that our name had better be blah-de-blah-de-blah-de-blah-de-blah octane, because that's the name that you will need to know for an 8-carbon chain. And like I said, I would be shocked if you ever needed to go above dodecane, or maybe tridecane. But the great thing is if you know undecane, dodecane, and tridecane, you get up to C19 for free, tetradecane, pentadecane, hexadecane, so forth. So, but I've never seen a question in OWL or anywhere that you would have to go above dodecane. Good, so next the rules state that you need to number the carbons such that you start closest to the first branch point. And that's a little bit ambiguous here because in both cases, it starts to branch at the second carbon in. So you can think of it one of 2 ways. Well, actually, let's just say this way. If you run into that situation, probably the best thing you can do is to put in both numbering systems. One of them will be right in the end. And as I said, you will be able to come up with an unambiguously best answer. So you just start numbering them. And you only number these ones if you only number the ones that are directly included in the chain. So 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8. And you don't need to worry. Exactly one of those 2 numberings will be correct, and it will be absolutely unambiguous when you're done. I've never seen a question. I don't think it's possible to make a question where they're ambiguous still. Does that sound good? Is that making sense so far? I'm just trying to assuage some potential fears. Let's see. Still some discussion of alcohols and carboxylic acids in chat, and that's a good point. Carboxylic acids are a good deal more acidic than alcohols. That's true. And when I say a good deal more, you're talking, probably 1 trillion times, 12, 13 orders of magnitude. It's very, very dramatic. Good. So now we need to look at what are the alkyl groups. And I've defined alkyl groups in the class notes. And again, we've talked about methyl, ethyl, the 2 propyl groups, and the 4 types of butyl groups. Those are, I think, the only ones you'll ever need. I've never seen one that needed, OWL will be OWL. Probably there's someone evil who uses a pentyl or a hexyl group there. But And again, I can't give you exact lines around exactly what you will need to know, exactly what the questions will look like. I can't do that. You'll just have to get in there and experiment. An owl will push you, probably to the limits and beyond. But the best way to learn it is to get in there and practice. Good. So let's see. So one of these two numbering systems is going to work. As things stand, I see two methyl groups on what's going to be either carbon 2 or 7. Do you agree these are CH3s? Can you see there's 3 hydrogens on each of them that we're not showing? And then we've got another methyl group here on what's going to be the other carbon 2 or 7, depending on which numbering system we use. By the way, I think already we can take a guess as to which of these two numbering systems we want to use. Remember, at the end, we want to get a name that has the lowest possible sum when you add up all the numbers in the name. And that's in my class notes. Lowest possible sum when you add up all the numbers in the name. That's what you want to aim for. And since with these two methyls, we're going to repeat the number, we're going to state it twice, 2, 2, because both of the methyls, they are different methyls from one another, and they're both directly attached to carbon 2. Well, I think we'd better use what I've given here as the red numbers. I'll show you what I mean. You're still going to be able to tell, even if you're not sure and you're worried, you're still going to be able to tell. But I think we'd better use the red numbers. That will mean that we have 2 methyl groups in carbon 2 and another one on carbon 7. Oh, and look at that. We've got on carbon 5, what's that called? CH2CH3. So a 2-carbon alkane is ethane. That's CH3CH3. What's CH3CH2? Ethyl. Yep. So you need to know these names of these smaller alkyl groups at least. Does that make sense? Is everyone at least clear in what they're going to have to know so far? Good. Okay, and we see that the ethyl group comes off of carbon 5 using the red numbering system. So let me actually keep that on red. So it looks to me like we're going to call this, well, actually, now we need to think what comes first, ethyl or methyl? And the answer is it's alphabetical. So E comes before M. So we want to call out the ethyl group first, 5-ethyl. And now we'll talk about the methyl groups, 2, 2, 7. And how do we say there's 3 methyl groups? Trimethyl. So you do need to know those Greek prefixes. They show up everywhere, so it's good to know them. 2, 2, 7, trimethyl, and then octane. That's all there is to it. So the 5-ethyl means that coming off of carbon 5, we've got CH3CH2. And we write 2, 2, 7 trimethyl in order to show that there are 3 methyl groups. 2 of them are in carbon 2. That's why we repeat the 2 to show that there's 2 different methyl groups coming off of that carbon, and a methyl group in carbon 7 as well. So that's one possible name. If we use the blue numbering system, what will we get? We'll get 277. Well, over here it'll be 277 trimethyl. Where's my ethyl group now? My ethyl group is on, oh yeah, on carbon 4. So it'll be 4-ethyl, 277 trimethyl octane. And now we add up all of the numbers in the name. 4 and 2 is 6. 6 and 14 is 20. Whoops, that's dreadful. Yep. And over here you've got 5 and 2 is 7, 2 more is 9, and 7 is 16. So I think it's clear. That's the best name. We'll go with that one. We won't go with that one, because 16 is less than 20. And again, I've never seen a case, everyone's always concerned, what if they're the same? I do not believe it's possible for them to be the same. I guess if they're the same, then either answer will be accepted for full credit. But I've never seen that happen. I don't believe it's possible. I think if you go through this method, you will always get one unambiguously best answer. And by the way, I just cannot answer all questions like this, but I do want you guys to be aware, partial credit is possible. You know, if it's close, certainly partial credit is possible. Partial credit is always at least an option on exam questions. But in order to get partial credit, I remember one of my colleagues at my previous school saying this, and I always liked what he said. In order to get partial credit, there must be something that's right. You know, we don't give points for effort. Good, so I mean, I would like to do 3 or 4 more of these, but I've got like 20 minutes to get through at least ethane and at least begin talking about butane and conformations. So I'm sorry I don't have more, I can't do more examples. I will say if you're having trouble with any of the AL questions, please feel free to bring them to office hours. I think you got my email that I'm starting up Saturday office hours also. So please don't hesitate. That's what I'm here for. Good, but hopefully that at least gives you guys the idea, that at least gives you guys, and I see a good question in chat, that at least gives you the idea of a place to start with all of this. Now, question in chat, why is 5 better than 4? How come I get to use the 5 here? Why don't I just use the 4 there? The answer is you have to use the consistent numbering for any one. You have to stay consistent to any one numbering of these. So I can't pick one number from the blue numbering and one number from the red numbering. You have to stay consistent. But even with using the 5 here, we still get a smaller sum. So we can be sure, that's the best answer. We can be confident about that. Now, candidly, in some ways, this answer isn't terrible, the second one. I could imagine worse answers than that. It would probably receive partial credit. Start to cover conformations of alkanes. And what I'll do is I'll just make a video at home, might be 15, 20 minutes in length, in which I go over some things about nomenclature of alkanes. We did cover that in my previous class, but we would probably be finishing up with that right about, first of all, which of these clocks is right? That says 12:19, that says 12:11. I think this one must be right. Usually, because sometimes that says like 3 in the morning. So, okay. Oh, they're saying 12:11. Thank you, chat. Okay, good. So let's. The other good news for the day, for those of you in chat are hearing this for the first time, the face shield has come in, and I think that's a heck of a lot better. I just feel like my voice is clearer. And also this is helpful to people who rely, at least to some degree, on lip reading. So now you have that option. And on top of it, at least you can see all my facial expressions, which that's why it's so hard. It's something I find difficult. I mean, you guys in particular, I just sort of mean in general in society, I can't see facial expressions. You know, I find myself, I'm in the supermarket and I smile at someone. They don't know I smiled at them. It's just weird, you know? But you know, it is what it is, and we're all working through this together. Excellent. So thank you for your patience. Let me see if I can't get up the materials for the clicker session. That will give me time to finish setting up, which I've almost done. There's our iClicker. So I've just got a couple questions for you today. I think I've largely figured this out. So basically the way it's going to work is the 2 questions will each be 1 point each. Whoops, tamu.edu. And then the other 8 points you'll just get for attendance. And the great thing is, it looks like I'm able to, wait a minute. What do you mean end class? We should have, in progress. Oh, okay, so then, where's my thing? I think I'd better end class and then restart it, because this is acting really weird. Progress. Oh, here we go. Well, let's see here. Let's give this a try. So first I need to share so that Those in chat can see the questions. So is this working? Can everyone see my sort of title slide for our clicker session? Hopefully you're all seeing the questions now. Excellent. So first question has to do with which of those is the correct curved arrow notation for that mechanism. Please do not put E. E is a wrong answer this time. There it is. Okay, so someone responded, so it's working. Excellent. Let me then, well, I can't really do anything while this is taking up the whole screen. That's fine. So as I was saying, I'll do a separate video for nomenclature of alkanes. Nomenclature of alkanes is really something you're going to mainly learn by practicing on your own. There's only so much that I can do for you in that category. But I can at least get you guys started with that and then get in there and practice, especially on the owls. And you know, owl is a little bit evil. They will, okay, maybe significantly evil. They will, oh, and in addition to all the comedy of errors today, I don't know where my glasses are. I also just realized I think I left my Microsoft Surface in the other classroom. I just don't know how this day could go worse. You know, thank God I didn't get into a car accident yet. What? Yeah, well, you know, exactly. It can always be worse. Good. So let's let that go another 30 seconds or so, just make sure everyone gets a chance to answer. Then we'll finish these up. And even though, like I said, my understanding is, if I recall correctly where we ended, we need to do some on nomenclature of alkanes, but I'll make a separate video for that at home. Yes? Do I like welding? I would be really bad. I'm really bad at anything having to do with fixing things. Why? Oh. If you wanted something yet worse to happen, yes, try me out at welding. That would definitely be worse. Oh, I see. Because of this, I get you now. Yeah. Yeah. All right. Well, let's call it there. So remember the rules that we've set for arrow pushing, which is basically the arrow needs to start where the electrons start and end where the electrons end. There are no exceptions. That's always going to be the way with owls. Oh, with arrows. Similar sounding word, actually. So it always starts where the electrons start and ends where the electrons end. Arrows are never used for movement, to show movement of atoms or to show movement of charges. They are always and only for electrons. And so, well, let's look at what happens over the course of this reaction. Looks like this aluminum compound is going to be our Lewis acid, not surprising. Aluminum, when it has a formal charge of 0, lacks an octet. It has only 6 electrons around it. So it wants to get another electron pair. And Cl2 is by no means the greatest Lewis base in the world, but we have no other choice here. So we're gonna donate an electron pair from any one of these 6 lone pairs on the Cl2 molecule, doesn't matter which. So that's where our arrow is gonna start, and it better end round and about the vicinity of the aluminum. Question in chat is, how do you know which one is the acid or base without the products? Well, I mean, I would expect you guys to know that boron and aluminum are electron poor because they lack an octet. And so the other one has to be the Lewis base. And generally, you can get a pretty good guess if it's a Bronsted-Lowry acid-base reaction also. So, well, it depends on which one is offering the electron pairs. Yes, but I think they're asking, how do you know which one is going to offer the electron pairs? So I'm saying, I think there's some good hints already based on finding the species that's electron poor. Good, so we want to start the arrow on any one of the 6 electron pairs on the chlorine molecule and end it round and about the vicinity of the aluminum atom. And I think B is the best choice for that. And again, any reasonable variation on this is fine. Why do both chlorines join the molecule? Well, again, in this case, we're given the structure of the product. The reason both chlorines join the molecule is if you break the bond, which would be shown this way, then you're going to leave behind Cl plus sitting by itself, which is a really weird species. It's not the sort of thing that you can generate easily. It's a very high energy species. So I think we're better putting the plus charge in chlorine, because then it at least obeys the octet rule. And true enough, chlorine with a plus charge is not that happy, but we're better off doing that because it at least obeys the octet rule. If both chlorines didn't join the molecule, then you'd be left with a chlorine atom that had only 6 electrons around it. And that's no good. I think given the choice, it's better to obey the octet rule. So I think the best answer is B. So I've learned I can grade this on the spot. Woohoo, that's cool. So next question I think is a little bit more straightforward. Which of the following is the generalized structure of a carboxylic acid? And I think there's one clearly best answer. Yeah, he's saying the bond between the chlorine was never broken, and that's true. But I think her question was, how would we know in the first place that that's going to be the case? So if you're given the product structures, which I think you usually will be, maybe not always, but usually, then it's straightforward. But if not, what I was doing was giving some hints as to how you could guess that a priori ahead of time. Yes. The question is this the modeling kit that's recommended for the class? Well, the one-word answer to your question actually is no, because this is the teacher kit. So, and this only cost me 35, 40 bucks. So you should get something, you know, the regular student kit. I don't think they go for significantly more than 15 or 20. Certainly don't spend a lot of money. I do recommend ones that look like this, you know, where you have the little balls and little plastic sticks for the bonds. I think they work the best. Good, we'll go about another 45 seconds or so. Is this how the questions will be structured for the test? Well, again, I've posted old exams. I cannot promise you that your exam questions will look exactly like this or exactly like what you see in the posted exams, but it at least gives you an idea of some questions that I've asked. But no, I make no promises that I will use this exact, I make no promises that I'll use this exact format. How do you know aluminum is electron poor? Oh, you're probably disappointed. No, don't worry about it. The way you know aluminum is electron poor is, yeah, when you make structures of aluminum, and boron also, by the way, what you find is that it's an exception to the octet rule. It only has 6 electrons around it, and it's in its neutral state. It can take on another electron pair, but then it is a formal charge of -1. And that really has a lot to do with the chemistry of both boron and aluminum, is that they're never happy. And if they have a formal charge of 0, they lack an octet. They can take on another electron pair and have the octet, but then they have a formal charge of -1. So they're just never happy. Good, so there might be some review to do there. No, that's not disappointing, that's completely fine. Good, so it looks like everyone's answered here. We'll cut that off. And hopefully this is fairly straightforward. All of these abbreviations are fine. You know, they all stand for something, but hopefully you'll agree that it's this one that's the best answer for a carboxylic acid. And you can also abbreviate it as RCOOH. That's also fine. The old exams are posted on eCampus. They're already there. Good, so either of those is fine, and you can use that abbreviation. If you wanted to write acetic acid as CH3CO2H, it's fine, and there's times that's entirely appropriate. Good, so I think A is the best answer. Let's see what you guys thought. Also A, by an overwhelming majority. Good, and the other 8 points are gonna come from attendance. And so it may take a few days for that to appear correctly on the reef cloud thing, but I'll need to go in there and fix it. But again, like I said, anything you see on eCampus will supersede what you see on the reef website, because it doesn't always look exactly the way I want it to. Good, so I think that's enough for that. As I said, with this class today, since we've lost some time, I plan to just go over the beginnings of alkane conformations. And then I'll put up a separate video on just to at least get you guys started on nomenclature of alkanes. But gotta get in there and practice. It's the only way to learn material like that. Good. So, yes, oh, that's right, I have a pen, thank goodness. Right, so I'll assume we've just finished up on naming alkanes. So conformations. What are conformations and why do we need to talk about them? Well, this chapter is about alkanes, about how they behave, what their reactivity is like. Spoiler alert, very low reactivity. Alkanes are pretty inert. There's very, very little you can do with them synthetically or in terms of any chemical reactions. One reaction you know already, combustion. Alkanes are, of course, very flammable. They combine rapidly with oxygen gas, O2, and in a complete combustion, your products will be CO2 and water. And those equations are generally quite easy to balance by inspection. You covered that in Gen Chem. Later on, we're also going to talk about the only really other thing that you can do with alkanes that I can think of anyway, which is halogenation. And we'll get to that later. That's another type of reaction. But there's very, very little that you can do with alkanes. They're quite inert chemically. But we also want to learn about other properties of alkane. This is going to help us understand molecules better so that we can learn what we need to know as we keep going on in successive chapters. And really this first part of Organic 1 is just getting the groundwork laid. And so this is part of the groundwork. And so one of the, oh, I just lost my train of thought, which, you know, you hit a certain age and that happens. Well, maybe I'll start this way. Something that I believe I've pointed out before about molecules in general, not just alkanes, is that molecules are not these stiff, rigid, unmoving pieces of furniture, but they're in constant motion. And one sort of motion that's available, ooh, shall we see if this works? Wouldn't this be cool? New share, so we go to advanced, we do content from second camera. Whee! There's our molecular tinker toys. Good, so, oh yeah, the camera is a little bit slow. Can I go over? Having trouble seeing where things actually go. I'm trying to get it away from the chat window. So the point is, with single bonds, we have full freedom of rotation around all single bonds. And that's always going to be the case for any single bond. Doesn't have to be a carbon-carbon single bond. Not so for double bonds. We do not have full freedom of rotation around pi bonds. And yes, of course, you can rotate around carbon-hydrogen bonds also. There's just not really anything that results from that. But as soon as you find being able to rotate around single bonds like this, it means that not all states are created equal. And it's these different states that you can get simply by rotating around a single bond. That's what we mean by conformations. So that's the definition of conformations. So these are not isomers. That's a different critter. That's different, you know, same molecular formula, but different arrangement of the different connectivity of the atoms. So that's a different animal than this. And actually, in this case, we're looking at ethane. Let me get it back on the camera, maybe. Why is this so hard? Well, so what is going on here? I'm just trying to figure out where everything is. Okay, I think I've got it now. So in the case of ethane, there are no other isomers. There's only one way you can put together 2 carbons and 6 hydrogens, and this is it. But there are 2 different conformations. In one of them, and we'll draw these pretty soon in a few different ways. In one of them, if you look straight down the carbon-carbon bond, then you find that one of the carbons is, well, eclipsing the other. Just in the same sense we talk about a solar eclipse or a lunar eclipse. And not only that, but also each pair of hydrogens on adjacent carbons eclipses another. It's directly behind it. Oh, and I already had the question of buying molecular modeling kits. This one I have here is the special teacher's modeling kit. And I think it cost me 35 or 40 bucks. And you certainly don't need to go that far. standard student modeling kits, I doubt you'll need to spend more than 15 or 20 bucks. Certainly don't spend a lot of money. Goodness knows you spend enough money already. But you should be able to get something perfectly serviceable for that price range, maybe on eBay, maybe on Amazon. Good. So that's one of the two conformations of ethane. And the other one, we turn 60 degrees around that central carbon-carbon bond, and now nothing is eclipsed. And so we call that the staggered conformation. So ethane is two conformations, eclipsed and staggered. And like I said, I'm going to spend most of the rest of the class besides this showing you how to draw these things. We have three different ways of doing so, none of which is any better than the other. But in the eclipsed conformation, what we find is that the electrons in the CH bonds are closer to one another in space. Dang it. They're closer to one another in space than you would find in the staggered conformation. And if these electron pairs in these bonds are closer together in space than they really need to be, that's going to lead to an increase in energy. And so, yeah, that's going to lead to an increase in energy. Why? Because electrons are all negatively charged, and like charges repel. So if we can relieve that electron-electron repulsion by going into the staggered conformation, that's going to lower the energy. And so this phenomenon of an energy increase or a decrease in stability, it's different ways of saying the same thing, that arises from electron-electron repulsion of electron pairs and bonds, that's what we're going to be talking about over the next few days and calling, it's known as torsional strain. And we'll get to that. We'll be using that term pretty regularly, probably for at least another 2 or 3 lectures. So we'll talk about that more. And the difference in energy between these two conformations is about 12 kilojoules per mole. Not that I really care if you memorize that. And you simply alternate between them, eclipsed, staggered, eclipsed. Oh, you don't want to look at my hands. Okay, I need to decide. Well, here, let me do this, and let me actually get that bloody thing on camera. Okay, so as long as I stay sort of on that part of the book, we're fine. Around that single bond, you just alternate between eclipsed and staggered and eclipsed and staggered and eclipsed and staggered, and it goes on and on forever. So, so those are the two conformations that we're talking about. Let me now switch to my whiteboard. Good. Oh, someone's here from my 255 class. Welcome, but this is Chem 227. You guys are 222, which is fine. You're more than happy to stick around. There's a lot of crossover, especially here at the earlier part. But we might not be in exactly the same place. Good. So now we can get back to this. So again, ethane, of course, CH3, there's a few different ways to show those different conformations. Let's start with, let me check my time. Let's start with the eclipsed conformation. One way, you're familiar with this, just using standard wedges and dots. Something like that. And you can see that we have those two bonds directly in front of and behind each other. Same thing with the two that are on wedges. Same thing with the two that are on dots. And again, remember what I'm trying my best to show here. My drawing isn't exactly perfect. I think it's pretty good. I could make it a little better if I redrew that one hydrogen. Maybe something like that. Probably just redrew exactly the same thing. So, yes. Oh, you can. This is just one way of doing it. The one looking straight down the bond, we're going to call that the Newman projection in just a moment. So there's other ways of doing it, and none of these ways is any better or more correct or any safer than the other. The way you know what to put is by what the question asks you to do. And all of these are ones we're going to be using later on in the class, so they're all worth learning. Are we supposed to do Newman projections? Yeah, and I think we'll have time. So this is one way of doing it, just with standard wedges and dots. And actually, I think it would be helpful if I showed you how the staggered conformation looks. This is, again, not the only correct way. But here, you want to make sure that your straight lines, which are your bonds that are in the plane, will be more like this, so that nothing's directly in front of nor behind anything else. And the rest of the molecule will follow from that. So this is just showing that using regular wedges and dots, which we've used a lot before. And again, the goal, let me say this, here is what you need to know about drawing wedges and dots, because I think this is what people fail to concentrate on. What you need to know is that what you're aiming for is to show bond angles of 109.5 degrees. That's what you're aiming for. The way you know that you have to do that is because these atoms are sp3 hybridized. And sp3 hybridized atoms adopt a tetrahedral shape. So we're aiming for 109.5 degrees. And I think I've already said this, I make an agreement with my students. I promise not to get out a protractor on you guys if you promise not to get one out on me. But I think you'll see I've done a pretty good job at, a good faith effort at aiming for 109.5 degrees. And that's what I would expect you to do too. That's not the only correct way to draw these. We'll get there though. Yes? Is there a reason why what? Yes, because is there a reason I inverted it? Yes, because you have to in order to go from staggered to eclipsed. With eclipsed ones, you can see how this part of the molecule is all in one plane, right? And that's represented by this over here. You can see they're all in the same plane. But then when you switch to eclipsed, it's those four atoms that are in the same plane. And the way you know that is, well, that's what we get in the staggered conformation. Now it's those four that are in a plane. And I could have picked other four, these four are all in a plane. Those four, or actually it's these four out in the plane, and it's this one and like that are in a plane. It's just easier to see with the straight line ones. So that's the reason that I inverted them, because it's a different conformation. Good, so this is only one way of showing it. Another pretty common way of showing conformations around a single bond uses what's called a sawhorse structure, a sawhorse projection. And I think they call it this, he asked if I liked welding. You could also ask if I like woodworking, which I don't do either, but I'm told that a sawhorse looks something like that. And again, you can see that we're showing that those two hydrogens are sitting directly in front of and behind each other. And it's just another way of drawing it. So these are your sawhorse projections, and these are your standard three-dimensional drawings with wedge bonds and dot bonds. But I'm only dwelling on the wedge and dot bond structures because I just want to make clear you guys do have to know how to draw structures with wedges and dots correctly. That's absolutely necessary. That's something that should have been covered at least a little bit in Gen Chem, but that's something we're going to be using a lot. It's not something you can do by memorizing pictures. You need to understand the geometry around that atom. Good. And how would we draw the sawhorse drawing of the staggered projection? Well, maybe something like this. I don't say it's the only correct way or is to look exactly like this. But now I'll make that other hydrogen pointing down, maybe something like that. That's just another way of showing it. And we're going to be using sawhorse drawings, by the way, quite a bit when we get to cyclohexane pretty soon. That's one of the more common ways of drawing cyclohexane. Good. And then someone asked about the Newman projection. That's yet another way of representing 3D structures. And the idea behind Newman projections is that we're going to put our eyeball here right in front of this central carbon-carbon bond and look directly down it. So we're doing a thing like this, or, oh yeah, that's actually fairly good. Something like that. And so as a result, we'll see, first of all, the carbon-hydrogen bonds going to the carbon in front.
And the way we represent bonds to the carbon in front is they're going to go to the center of the diagram. Something like that. And what about the bonds that are in the back? Well, we represent those by lines that are broken by the circle. And it's always somewhat tricky to draw eclipsed conformations. You have to kind of do the best you can. Something like that would be perfectly acceptable. It's a little easier to draw the Newman projection of a, that's not really a circle, is it? It's a little easier to do so for a staggered conformation. So there, what we would show, again, these bonds are in front. And now if, again, you imagine you've got your eyeball over here, these ones are in back. They're kind of bisecting. Something like that would be an acceptable Newman projection. The model of the Newman projection is over here. You can use the same model. And again, this one is eclipsed, so you can see that the hydrogens lie directly behind each other. Whereas if we were to go like this, then you would get a model for the staggered conformation. And I think you can see pretty clearly how the hydrogens in back stick kind of in between the hydrogens in front. And that relieves that eclipsed conformation. That relieves the so-called torsional strain. Chat can't see. Oh, that's right. I guess I can only do one at once. Let's see. Okay, there's your second camera. So you can use these models to help you see what to put for a Newman projection. I just can't get directions. First of all, there's a delay. Okay, we'll go with that. So here is what your eclipsed conformation would be like. And by the way, under normal conditions, I have like big models with big Nerf balls that are kind of easy to see in the back of the room. That's what I normally use, but I was hoping this doc cam would be a little more successful than that. So hopefully, as well as in chat, you can now see that any two hydrogens are lying directly behind and in front of one another. And when we go to the staggered conformation, that torsional strain is relieved. Now you don't have these electron pairs close together in space any longer. They're further apart in the eclipsed conformation. Sorry, in the staggered conformation. And so that's why the staggered conformation is lower in energy than the eclipsed conformation. It's because you get rid of that problem. And so talking about what the circle represents. And actually, in my experience, people, I don't know that there's one correct way. Some people find it easier to learn what they need to know if they think of the circle as the front carbon. Others find it easier to think of the circle as the back carbon. Certainly, the bonds to the front carbon are going to be these that go to the center. Those are always going to be the bonds to the front carbon, whereas the bonds to the back carbon are kind of broken up by that circle. So that's always going to be true. The way you think about that, I think I can leave that up to you. Use whichever way of you can think. If you think of the circle as the front carbon, that's fine. If you think of it as the back carbon, that's fine. I can't really say either of those two is more correct than the other. So do whatever works for your learning style. As long as you understand that the bonds to the front carbon are going to end in the center and the bonds to the back carbon are going to be broken up by that circle. Another thing you should be aware of is it doesn't have to look exactly like this. You could also have drawn the eclipsed conformation kind of with the whole molecule turned 60 degrees, something like this. Perfectly fine. It's just another way of drawing the same thing. Not only would I not take off points I wouldn't even notice. Make sense? Yeah, either was perfectly fine for drawing the staggered conformation. Now, what about the energy diagram? Well, the way we normally do that is, could be one of the worst sets of axes I've ever drawn. And again, we're being relatively qualitative here. In an energy diagram, you want energy in some form on the vertical axis. It might say E, it might say delta E, it might say delta G, it might say delta H. Doesn't really matter. They're all going to be pretty close to one another, in fact. And normally we have reaction coordinate on the horizontal axis, which is basically kind of like time. But I think the most useful way to do it here is to think of relative angles. So 0 degrees, 60, 120, 180, 240. And now how do you know which is going to be 0? Is that going to be eclipsed or staggered? Well, I guess it depends on the setup of the question. I wouldn't say that 0 degrees absolutely represents either of the two. You got to kind of pick one. It doesn't really matter. Maybe for us today, the 0 degrees is going to be the eclipsed conformation, which is going to be higher in energy, relatively speaking. And maybe 60 degrees is the staggered conformation. And so that will then keep alternating. Every 60 degrees, you'll get another eclipsed. Every 60 degrees, you'll get another staggered, and on and on and on. And the way you know that is, again, I think you can make that clear by looking at the model. Every 60-degree turn, there's staggered, there's eclipsed, there's staggered, there's eclipsed, there's staggered, and so on. And those really are just relative terms. They just alternate every 60 degrees. And in the end, you have essentially a sine wave. That's very much what it looks like. So, whoops, whoa. Maybe let's try it like this. Do the best I can. It's close, something like that. Now, as it turns out, that energy difference is roughly 12 kilojoules per mole, or maybe roughly 3 kilocalories per mole. I don't really care if you memorize that number, but it is known, that's the difference. And it's not a large energy difference, but it's also not nothing. It means that at any given time in a sample of ethane, the vast majority is going to be in the staggered conformation. So, so far so good? Question so far, yes. Higher energy means it's eclipsed. And the way you know that is higher energy means less stable. So the higher energy one is going to be the eclipsed conformation. And the lower energy one is going to be the staggered conformation. So that's another thing you guys need to know from Gen Chem. Higher energy, less stable, same thing. Lower energy, more stable, same thing. Is that kind of what you meant? Just want to make sure. Good. So as it turns out, even if you make the molecule a little larger by going, let's say, from, I'm going to use this as kind of a segue into butane, which we're going to mainly talk about on Wednesday, if I live that long, the way this day is going so far. Good night. Okay, so here's our propane. And if you consider any one of these carbon-carbon bonds, it turns out propane is no more interesting than ethane in terms of conformations. You've got an eclipsed conformation in which the methyl group is going to be eclipsing one of the hydrogens, and you've got the staggered conformation. And that's it. So those are the only two possibilities for propane. And so the energy diagram for propane would look very much like the energy diagram for ethane. The only difference being this would no longer be 12 kilojoules per mole. It would probably be higher. I don't know if it's 18 or 20 or what it might be. And this is true for a wide variety of other molecules. You could imagine changing any one of the H's in ethane to pretty much whatever you like, a chlorine, an OH. You'll get a molecule that's pretty much the same idea as ethane in terms of its conformations. And so that, however, goes out the window when you go to butane. Because, I'll just lay that there, because with butane, now we have more than two conformations. Turns out there's two different staggered conformations. We're going to call those anti and gauche in the next lecture. And there's two different eclipsed conformations also. And so that's next time, since I'm largely running out of time here. So like I said, we'll pick up with that on Wednesday. You can expect a separate lecture besides this that I'll just record from my laptop or from my Microsoft Surface if someone didn't take it because I left it in the classroom. Jeez, what a day. So other than that, everyone please stay safe because it's looking like one of those days. But other than that, I'll see you all on Wednesday.